that is of long wavelength, low frequency, low energy, whereas something like this is going to be of higher energy, higher frequency, lower wavelength. All right, now the math on this gets pretty tricky. It can be, but to begin with, there are just a couple of equations that you have to know, both of which are given to you on the AP test. So the two equations that you're going to have to work with on this are going to be these guys here, that the speed of light is equal to the wavelength times the frequency. So again, all of that is over here. That's frequency and that's wavelength. If you've not seen it represented this way before, this guy here is wavelength and this guy here is frequency. Okay? And the speed of light is 2.998 times 10 to the 8th meters per second. And then the other aspect of this is the energy equation. We'll come back to him. All right? By the way, you'll also might need to know that a meter is 10 to the 9th nanometers. That's going to be important later on. So, electromagnetic spectrum has a pretty wide range from radio waves over to gamma rays, but they are all basically governed by this equation. So, first, what is the frequency of a photon of radio waves that has a wavelength of 2 times 10 to the 3rd meters? All right, let's check this guy out. So, our equation is that the speed of light is equal to the wavelength times the frequency. So the speed of light is 2.998 times 10 to the 8th, and that's in meters per second. And that's going to be equal to the wavelength, which I gave you as 2 times 10 to the 3rd meters, times the frequency. So this is a very simple plug and chug. So plug your numbers in, chug them through the calculator. The frequency of this guy is just 1.5 times 10 to the 5th, and that's in inverse seconds. So that's really not too tough. Our next one says, what is the wavelength of a photon of gamma waves that has a frequency of 5 times 10 to the 12th inverse seconds? So this is the same equation. The speed of light is equal to the wavelength times the frequency. So 2.998 times 10 to the 8th meters per second is going to be equal to the wavelength times the frequency, which they gave you as 5 times 10 to the 12th, and that's in inverse seconds. And so consequently, the wavelength, if you do the math on that, turns out to be about 5.99 times 10 to the negative 5th, and that's in meters. That's there. Okay? So, easy breezy, mac and cheesy. Now, your second equation that you're going to need to know is the energy equation. So in the energy equation, the energy, which is here, right, is going to be proportional to the frequency, which is this guy here, but it can be made equal if you include this guy here, which is h, which is known as Planck's constant. And Planck's constant is this number here that you don't have to memorize, 6.626 times 10 to the negative 34th joule seconds. So that is that number that goes right here in this equation. So again, this is just a simple 3-variable equation where we are solving for things, except that it's proportional to the frequency. So this one here says, what is the energy of a photon of radio waves that has a wavelength of 2 times 10 to the 3rd meters? Well, this is the same problem as before, except I'm asking you for the energy. So the energy is going to be equal to h times the frequency, or the energy is going to be equal to 6.626 times 10 to the negative 34th, and that's in joule seconds. And all we need now is the frequency here, except they gave us the wavelength. But we did this problem. We did this problem up here, and we already solved for the frequency. This is the frequency. So all we have to do is copy that and then put it into our equation here. So that is your frequency from the problem before. And we plug and we chug and we go to town. So this is going to be equal to about 9.94 times 10 to the negative 29th, and that's in joules. And again, that's for a single photon of that. All right. Our next one says, what is the energy of a photon of gamma waves that has the frequency of that? This is the same equation. You want energy, so energy is going to be equal to h times the frequency, or energy is going to be equal to 6.626 times 10 to the negative 34th, and that's joule seconds. And we now need the frequency. Oh, they gave us the frequency in this one, so all we have to do is plug that one in. 5 times 10 to the 12th, and that's in inverse seconds. So our energy should be about 3.31 times 10 to the negative 21st, and that's in joules for that individual photon that's there. Now, all of these equations that we are working with here, they all work for a single photon. The problem is that most of the time you don't ever deal with a single photon, you deal with spagillions of them. But in chemistry, we don't call them spagillions, we call big groups of things by a convenient grouping called a mole. So remember that a mole is Avogadro's number, which is 6.022 times 10 to the 23rd, whatevers per mole. So they could very well ask you to solve the same problem, except that they could do it for a mole of photons. So all you have to do is do the exact same problem all the way through, and at the end make sure that you convert it into a mole of them by using Avogadro's number. So this problem here, last one, says what is the energy in kilojoules of a mole of photons that has a wavelength of that? All right, fine. Well, they gave us wavelength, except that they gave us the wavelength in nanometers. So here are those nanometer things again. So remember that 1 meter is equal 10 to the 9th nanometers, or if you'd prefer, 1 nanometer is equal to 10 to the negative 9th meters. Both of those things are true. You are free to use those for substitution anytime that you'd like. So for our first one here, we're going to use this equation because we need the frequency. So we're going to start with C is equal to the wavelength times the frequency. So the C is 2.998 times 10 to the 8th, and that's in meters per second. And that's going to be equal to the wavelength. Now the wavelength is 700 nanometers, but again, please note that your unit here is meters and your unit here is nanometers, so that cannot be. They both have to be the same. So I'm going to go ahead and take this 700 and turn it into meters by remembering that every nanometer is just 10 to the negative 9th meters. So instead of 700 nanometers that I started with, I'm just going to replace that with 700 times 10 to the negative 9th meters. Easy. So now I've got them both in meters. And now this is going to be multiplied by the frequency. So if I plug those numbers in, I go ahead and I then discover that the frequency should be about 4.28 times 10 to the 14th, and that's in inverse seconds. Except they don't want frequency, they want the energy. No problem. We'll just go ahead and use our second equation. And our second equation is that E is equal to h times the frequency, which I now have. So my energy is going to be equal to 6.626 times 10 to the negative 34th, and that's in joule seconds. I'm going to multiply that by my frequency, which is 4.28 times 10 to the 14th inverse seconds. And after I end up with the math on that, I get about 2.84 times 10 to the negative 19th joules, except that's not my answer. That is for a single photon, because remember, these equations can only be used for a single photon. So it doesn't want that, it wants it for a mole of photons. It said so up here, it wants a mole of photons. At this point, now it's simple. If I have 2.84 times 10 to the negative 19th joules, and that's for one photon, remember that there are 6.022 times 10 to the 23rd of anything, photons included, for every mole. So my photons cancel. So all I have to do is multiply it by Avogadro's number, and I got my answer. My calculator tells me that it's about 170,894 joules, which is fine, except that they wanted the answer in kilojoules. So kilo is 1,000, so this is going to be about 171 rounded up